You are most welcome. Today we are going to look at a scenario item about Hooke's law. It's basically about elasticity of a spring. We've been given a scenario item. If I may read through, it is saying on one rainy day, the trader's umbrella was blown off by strong winds. The mechanic discovered that the spring of force constant ranging from 18 Newton per meter to 22 Newton per meter, the umbrella was destroyed and needed replacement. The trader bought a new spring without specification from a nearby hardware and approached you for help task. You are provided with a spring from the lab with similar properties as the one bought by the trader. Advise the trader whether it can work in the umbrella or it will not. So that is our scenario item, and we are basically tasked to carry out an investigation to see if the umbrella will be replaced with the provided spring. And so what you are going to move on is, first of all, generating the flow of the practical, and thereby we have the item, we have the variables, we have the hypothesis and the materials. So in the aim we've got an aim saying an experiment to determine the force constant of the spring provided so as to determine if it is suitable to be replaced in the umbrella. You realize there is a reason as to why we are carrying out the experiment, and that reason is for us to replace it in the umbrella. So never forget to attach that reason. We move on to the variables. We have three of them: independent, dependent, and controlled. Under independent, there is mass, because it is going to be it is already generated values. You are the one who is going to generate them. Mass of the sorted masses and force F. Then under dependent, we have new position of the pointer and extension E of the spring. Lastly, controlled variables, you have got thickness of the spring, that one will not change. We've got initial position of the pointer, that is our P naught, and then the mass of the spring, and many more others, but you can put only one is enough. There's no need to put all of them, but I've just put them for study purposes. Move on to the hypothesis. Hypothesis, this is the prediction for our experiment, and our prediction, we are saying the force constant of the spring is between 18 Newton per meter to 22 Newton per meter, so as to be replaced in the umbrella. And then we have got materials. We have the retort stand, the spring, the 6 masses of 50 grams, meter rule, and the pointer. And we move on now to our next flow of the practical, and that will be the procedures. Under procedures, we've got the experimental setup. In fact, what I've forgotten, even the materials are under procedures, so you choose where to put it as long as you've included them. Under this, we're having experimental setup. As we can look at it, there it is. Endeavor to always draw a talking diagram, and also draw a neat one, well labeled. As you can look at it, there it is. Then we proceeding on now to the steps. The steps we are having: step number 1, that is the apparatus we set up as shown above. Always refer to as to why you set up the apparatus. Then after setting up the apparatus, we noted the initial position of the pointer. In other words, the initial position of the pointer was noted, or was read and recorded as P equals to 49.4 centimeters. Then after that, we went on to another procedure, which is procedure C, a standard mass M was suspended at the lower end of the spring. Then the new position of the pointer was read and recorded. The new position of the pointer was read and recorded. And in the first case, we recorded as 52.5 centimeters. After that, we moved on to calculate for the extension using the formula P1 minus P0. That is the new position of the pointer minus the initial position of the pointer to give us the extension. Procedure G, it says procedures C to E were repeated for different masses of M equals to 0.10, 0.15, 0.20, 0.25, and 0.30 kilograms. Remember, I've been given 50 grams, but when you convert them to kilograms, that's what you'll be getting, and that's what you're going to be using. Procedure H, the results were then put into a suitable table, including values of the force F in brackets N, and also the extension in meters. You realize our extension, you've been getting it in centimeters, so we have to include the column. Here we're going to change it in meters. And then why are we changing it to meters? To simplify our work. Otherwise, if you leave it in centimeters, yes, you will plot and come out with the results, but they will become a challenge for you. So the best is for us to first convert it from here before you move on. Procedure I. After that, we plot a graph of F against E, and we obtain its slope. After obtaining the slope, we have to come up with a relation between the slope and the force constant, where we are saying the force constant K of the spring provided was determined from K equals to S. Where are we getting this? This is theory. Go back to your notes and you will get to know why is K equals to S. If you don't know how to get it, please comment and we shall move on with it.
Continuing on, this I'm having the 6 grams, 50 grams masses, 6 of them, and I'm having the spring, the meter rule, and then the tote stand. When I set up the apparatus, my initial position of the pointer is at 49.4. I'll note that somewhere. And then I begin hanging on the masses, beginning with 50 grams. So beginning with 50 grams, I put on the mass hanger, and it is reading at this point. It is giving me 52.5. When I put on the second one, giving 100 grams, it will be giving us our new position of the pointer is at 54.8. And I put on the third one, that is 150 grams or 1.5 kilogram. It is at 57.2. Putting on another one of 50 grams, it will stretch to 59.8 at this point here. 59.8. Then I put on the 50th mass. It is at 61.5. And then lastly, the 60th mass, giving us a total of 300 grams, which is 0.3 kilogram. and at this point it is giving the new position of 63.6. And afterwards I remove off the spring in order for it not to lose its elasticity. And then we proceed on with the graph work and presentation of data. When it comes to graph work, this is what you're going to do. You're going to plot a graph of F against E, meaning our F will be on the vertical axis and our E will be on the horizontal axis. And what you're remaining with is to demarcate the axes. But before we demarcate, we are going to first get the graph, the scale for the graph. When you go to the vertical, since we are having values of 0.5 newtons and 1.0, 1.5, meaning there is a systematic scale already, which we shall just indicate. And therefore I'm going to begin indicating at this point like this. Demarcate this every 2 centimeters. So I will begin with 0.00. I will use a scale of 0.5. So I will begin at 0.5. This will be 1.0, 1.5, 2.0, 2.5, and lastly 3. 0.0, then 0.5. Since all our values are all catered within the range of the scale, we can stop there. Then when it comes to the horizontal, our values we are having are not having a systematic scale or a standard scale. Now what you are going to do is to first find a scale. And my highest, for us to find the scale for the horizontal, now I'm using this paper. This is your side work. So I can say horizontal scale. It will be obtained from us getting the highest value in the column of extension, which is E, minus the lowest value in the same column, and then divided by 8 big boxes. Now when you look at your table, our highest value are having 0.142 minus our lowest value, which is 0.031. Then the whole of this divided by 8. So when I press in the calculator, I will have 0.142 minus 0.031 equals, then divided by 8, and I'm getting 0.01. I'm getting 0.01, 0.013875. Now, according to the standard scales that we always have in physics, we have a scale of from 1 and then 2 and then 5. If I move downwards, I can have 0.1, 0.2, 0.5, or 0.01, 0.02, and then 0.05. Now looking at our value we've gotten up here, I realize it is falling between 0.01 and 0.02. So we shall not take the least, which is 0.01, but rather we shall go with the highest, which is 0.02, meaning our scale is going to be, in this case, 0.002. So I come back and I demarcate from here. I can choose to begin at 0. If I begin at 0, let me see. If I begin at 0, meaning I have 0, 0.2, 0.4, and 0.6, 0.8, and then 1, 1.2, and then 1.4, meaning our 1.42 will be catered for somewhere here, which is fine. So I can choose to begin at 0, I can choose to begin at 0.2, since my lowest value is 0.03, meaning my 0.02 will be less. So I can begin at 0.02, and then I put 0.04, 0.06, 0.08, then 0.10, then 0.12, 0.14, 0.116, and so on and so on. And therefore I've marked my graph. Now, so we are now going to plot the values, and when it comes to plotting, different from the vertical axis, the one for force, where its values are already on the axis, for instance 0.5, 1.0, 1.5, and etc. On the horizontal axis it is kind of different in that its values are not on the axis. Now what are you going to do? Let's look at what we call how to plot a value. When it comes to plotting the value, we get what we call the value to be plotted. I can say value to be plotted minus the starting value, and then the whole of this divided by what one small square represents. I can say one small square. Looking at the horizontal axis, our scale is 0.05, 0.02, and our scale is 0.02. Our scale is 0.02, and what you're going to do is you first get what one small square represents. If I say that 10 small square equals to 0.02, what one small square represents equals 0.02 divided by 10 equals to 0.002. So it means that every value I'm going to plot, for instance, I'm having my first value is 0.03. I'm going to get this value. I subtract minus the beginning value on the horizontal. Our beginning value on the horizontal is 0.02. Then after getting that, the whole of this are divided by 0. This, which is 0.002. When I subtract, I will get 5.5 small squares. So I come and look for them up, and I plot them 5.5. It means it will be somewhere here. It is plotting with this. I continue on to another value, 0.054 minus 0.02, 0.02 divided by 0.002. I'm getting 17 small squares. I come and count 17 small squares from the beginning. So I'll be counting from here up to here. There are 5, then there are 10, and I add on plus 7, which are somewhere here. I move upwards, it will be up to this point here. And that is then next is plotting 0.078. I subtract minus 0.02 and I divide by 0.002, giving us how many? Sorry, 0.078 minus 0.02 divided by 0.002. I'll count 29 small squares. That is the third one. So I count, these are 10, 20, I count up to 29. 29 is somewhere here. And it will be coinciding with 1.5. So continuing on to the fourth value, which is 0.1, I'll get 0.104 minus 0.02 divided by 0.002. This will be 0.104 minus 0.02 divided by 0.002, giving us 42 small squares. I come and count 42 small squares. These are 10, 20, 30, 40, and 42. It will be here, and it will be coinciding with the 2.0 newtons. And then the second last one, which is 0.12 minus 0.02 divided by 0.002, I get 50.5. I count 10, 20, 30, 40, 50. 50. Then the 51st small square, which I divide it a half, and that will be at 2.5. And we are remaining with the last one, which is 0.142 minus 0.02 divided by 0.002, giving us 61 small squares. I count 61. These are 10, 20, 30, 40, 50, 60. 61 is here. So 61, I move upwards up to here, which is 0.0. And that is our graph. Now we are remaining with getting the line of best fit. How do I get the line of best fit? So when it comes to getting the line of best fit, we are going to divide these points into equal parts. Let's say we are going to draw the line in such a way that it leaves equal points on either sides of the line. For instance, if I put my line to pass through this, you realize it is going to leave out, it is going to pass through this, but I have to fix it such that it passes very well. If I put it like this, and you realize it will pass through this, it will touch this one and also pass it through this one, meaning it has left out this and this other one, which is a fair way to go. So if I make my line of best fit, we go up to that way. It has passed through this one and this point, but it is touching this one, it is touching this one. It has left out this and this, which is good. Now what next from there is to draw the triangle, which is going to help us to get the slope of the graph. Now the triangle, you come and look through these points at the end. Where is this line passing? In the middle. You realize it is passing. I may take this. There is this point here. There is this point here. There is this one. There is I think on those three. There is this one here. So you choose which one is easy for you to take. I can choose to take on this one here. I can choose to take on this one. Let me take this. So I draw the triangle from here, and I dot it downwards. Then also do the same. I come and look out this other point outside here. You realize it is coinciding at this point here. This one, where I can take on this other point. And so I draw my triangle to meet the other side, and this one like this, and also downwards like that. Still, even this other side, come and make this line to meet the y-axis. I dot them. The lines that meet the axis are dotted. And there I'm having my right angle triangle. Here we go. What is remaining is for us to get these coordinates. This one here. That will be the x2, y2, and then x1, y1. x2, what will it be? I come down here. Where is it reaching? Is it? As we realize it is reaching at 1.6, at 0.16. So I can say 0.16. And then how about this other side? This one, it is reaching at that point. But how can we write it? We come back. We know that from here to here there are 10 small squares, but those 10 small squares are equivalent to 0.5, meaning one small square equals to 0.5 divided by 10, giving us 0.05. So I can just say, for me to read this value, it will be equivalent to 0.0 plus into brackets. How many are they? From here, there are 8 small squares. And then I multiply by 0.05. That value will be equivalent to 3.0 plus into brackets 8 times 0.05. We are getting 3.4, meaning my y2 is 3.4. Are we there? Yes, we are good to go. Then when it comes to x1, y1, I will still do the same. I read this value. Now for this one down here, for me to read this value here, it will be equivalent to, you realize there are only 3 small squares from the start, meaning it will be 3 times 0.002, giving us 0.006. So this is 0.006 minus r. Then our y2 will be equivalent to, how many are they? There are 7 small squares. Our y will be 7 times 0.05, giving us 7 times 0.05, giving us 0.05, and that will be the y1. And that is the end of our graph work. So what we are remaining with is to get the slope. So we are proceeding on to calculation of the slope S. And calculation of the slope will be obtained from change in f divided by change in e. Change in f, it means that we are getting a difference in the values of f, which is the force, divided by the difference in the values of of the extension, which is e. And back to our graph, we realize that we got these values, whereby we are saying our y2, the would-be y2, which is 0.4 minus 0.05 y1, divided by 0.16 minus 0.006, which is x2 minus x1. We are not writing those values because
they may not mean much as long as as long as the formula is enough. The repetition, it is up to you. Okay, we continue. Now we've gotten our values as 3.1 divided by 0.154, and the result we are getting in the calculator is 20.1 Newton per meter, which we are approximating to 20 Newton per meter. Why are we approximating? This is the rule of standard figures. Check the video about standard figures and see how do they operate. Okay, so after that we shall move on to now relating the slope to the value of the force constant, which is K. And from the equation we are getting that K equals to S, therefore K equals to 20 Newton per meter. Possible sources of errors. Errors may arose due to parallax. Parallax, it means that you didn't see where the value, so you read it the other way around where it did not come very clear. That could arise an error. Another one is overstretched springs, and then also unstable checking of the restart stand. Yeah, it might have been not well checked. It also arises the error. So we also state the mitigations or precautions of the errors identified. Number one, how do we mitigate the parallax error? We mitigate it by positioning the eyes at right angles to the scale of the meter being read, meaning you don't read it from down, you don't read it from up, but rather at right angles or in a straight line to that value. Using springs in good conditions and avoid overloading masses in the springs, and also removing masses from the springs immediately after taking the reading. That also should be mitigated so as to minimize the error of overstretched spring. Then lastly, using stable retort stands and ensuring that the working table is very fine. If your table is shaking, it will also give you wrong values. So it should be very flat on a flat surface, and that is it. Then we shall move on. Now we come to the conclusion. The conclusion will relate the conclusion to the hypothesis. It is the hypothesis that gives us our conclusion. And how do we conclude? We conclude and say, since our force constant of the spring is 20 Newton per meter, which is in the range of 18 to 22 Newtons per meter, therefore the hypothesis is true. That is good. Then what did you advise basing on that hypothesis? We advise that the spring can be replaced in the umbrella, and that is the end of the practical. Thank you very much for watching. I remain Aaron the Teacher. Find me at my YouTube channel, Aaron the Teacher. Please subscribe, like, comment, and share.